Hello, everyone. Thank you so much for braving the lovely weather we've been having out to come join us at this week's monthly Sky Talk. So it's been a very exciting time for astronomy recently. We just had the eclipse, and the subject of this talk is going to be about the next exciting viewing experience. So the presenter of our talk is Dr. Wilhelm. He's one of our professors here. He does research with our Lyrae stars and does research in part using our telescope at our very own observatory. So without further ado, you can go ahead and get started. Oh.
Okay. Well, hello. It's been a big week for astronomy. I hope that you all got a chance to see the eclipse, maybe the total eclipse if you made it there. So while we were getting ready to prepare MacAdam Observatory and everything, while we were getting ready to prepare for the solar eclipse, this was sort of at the end of March, there came this announcement that was kind of in the press. You did a lot of you could find it very easily. It would come up that we're going to have a new star that we'll be able to see in the sky. It'll be a very short period of time, but the name of it is T Coronae Borealis, or T Bore. That's what people like to call it. It's a recurring nova, and I'll tell you all about this as we go along through the talk. So my pictures here, sort of this is kind of the outline of my talk, what I have up here for the pictures. So when I start out, I want to share with everybody what was that?
Really nice projector.
Okay. I want to share with everybody how to see this nova. And here's the thing, this is really unusual. It's going to be, it's a recurring nova. So we know it happens about every 78 to 8 years. So people were anticipating that this would happen. But when it brightens up, it's going to be about a second magnitude star. Okay. So just for comparison, the North Star Polaris is a second magnitude star. Okay, now Polaris isn't the brightest star in the sky, but if you know where to look, you can easily find the North Star, and this star is going to be about that bright. Okay, it won't last too long, but when it occurs, it's really neat because here's this star that's going to all of a sudden appear. So we're really lucky because this kind of outburst, this kind of eruption, typically doesn't, it's not predictable usually. People kind of know, just like I said, they knew it would be coming. But usually what happens is all of a sudden somebody notices, there's a nova going off. And then everybody hears about it, and then you go, you might run out and, try to see if you can see the nova. And most of them are so faint that you would need binoculars or telescopes to see, even when they're bright, right? So this happens to be a really bright one. So what's really special about this is that we have time, right? We know it's coming, and we can prepare. And what's really great is this first slide over here, where I'm showing this. I want to spend just a little bit of time showing you how to find it. Okay, how to find Coronae Borealis, how to realize where this is. And what's neat about that, there's a number of second magnitude stars in the sky. Okay, if you're totally uninitiated and all of a sudden you hear, oh, the nova went off, right? Well, I got to go outside and look. Well, what would happen is that you go out and you might see it, but you might not appreciate it as much, right? It might be, oh, it's that star. I guess I see that star. But what I want to do is try to prepare everybody so that you know where to look. And since we have hopefully a little bit of time, it could erupt tonight. But if we have a little bit of time, you can prepare yourself. You can go out, you can look at Coronae Borealis, you can see what it looks like. And then when the event happens, all of a sudden it's going to be like, look at that star. It's this new star in the sky. This doesn't happen very often, right? Where there's a new star in the sky. Okay, so that's going to be the first part of my talk. I'm just going to spend a little bit of time doing that, and then I'll spend a little time over here talking about what the nova is and how this works, what's the mechanism, how it erupts and whatnot. And then I want to also show some data from the person that's mainly responsible for the prediction is Dr. Brad Schaefer at LSU, and he released this paper in 2023, and he's given some talks on it, which I watched to help prepare myself. And so we'll look at the data, and I can show you why we think it's going to happen really, really soon. Really, really soon, meaning in the next, I mean, like I said, it could happen tonight, which would be bad because we kind of missed the brightening, right? But the other thing is that it could happen in the next few months. Okay, so we don't know exactly when, but we know it's going to happen. All right, so I'm going to show you some of this so that you can understand how this prediction was made and why it's sure. And then I'm going to end by talking a little bit about MacAdam Observatory, because we're going to try to do some observations of this, and we're changing our website a little bit. And what we want to do is when we do observations with the telescope, and especially beginning with this, we're going to post them so that if we observe one night, then by the next day we hope to post what we saw, and we'll just keep going along with that and keep updating it every time. And there is a chance, if we're lucky, that we might be able to see it beginning to brighten up and send out the warning it's going to happen really soon. Okay, that's really going to be lucky because, you know, there's a lot of nights like this where it's all cloudy. so you know, but what we're going to do is so I'm going to show you some of this, and I also want to invite you to participate in this, especially in finding the explosion. Okay, so I'll show you some stuff about that also. Okay, so let's get started here. So this is, how do I move my little face here? There we go. Good. So this is Nova Centauri. It was a nova in Centaurus, which is a southern constellation, and this happened in 2009. So I just picked this just so that you could see sort of what's, oh, I need to stay over here. What's happening here. So in this image, it's quiescent. So the star system is very faint. And then it went through some kind of what they call a dwarf nova, which are kind of smaller explosions. And you'd have to look really, really close, but there's a little blue dot here. So they actually saw this in 2009. And then of course this is the explosion, right? So you can see this nova brightening up and then fading back away here in the end. Okay, so this is something like what we should expect. Okay, so this erupts every 78 to 8 years. The last eruption was 1946, so we're definitely coming up on time. What I wanted to show you now, this may fail, so I found this really nice sort of simulation of a nova explosion, and unfortunately it's on a NASA website, and it was working great yesterday, and I put it into my talk, and the last couple hours, just when I went through the talk one more time, it comes up saying the NASA server is down. So this may not work, but let me just show you. We'll keep our fingers crossed. Maybe it'll work.
Might have to hit escape. Yeah.
Oh yeah. No, that's a bad sign. Yeah, I'm not sure it's going to work.
That's before it explodes. It just doesn't look like anything.
Yeah, it's just very, yeah, service unavailable. Okay, so they're down. So I'll stop that.
They knew you were teaching.
I guess they did. Anyway, what this shows, so if you think of a star, you think of it exploding. I mean, you not exploding, the star itself won't explode, but there's going to be a thermonuclear explosion on the surface of the star, and you might think of it as this big ball, right? But it turns out that looking at another nova using space X-ray telescopes and UV and other telescopes that they were able to throw at this, they can see that it wasn't a nice homogeneous explosion. So I'm trying to do the simulation. And instead, it kind of comes off. It does come off slowly. There's a first an explosion, and then it kind of comes off slowly. And then there's secondary explosions that come out along the poles. So this causes a lot of shock, and these ones that come out along the poles are going like 5 times faster, about 5 million miles an hour. The ejecta is coming out. The first stuff is about 1 million. So when this really fast eruption runs into the slower one, then you get shock waves like a plane going at supersonic speeds, right? So you get a lot of light out of there. So that'll be important later when I show you some of the data, because at least I think this might be in part what's being seen in the data. Anyway, imagine you saw this really cool animation with an explosion. Okay, so I want to tell you where this is, Corona Borealis. So let me see if I can pull this off. So Stellarium's a really nice planetarium software. It's free download. You can do all kinds of cool things with it. So I just want to show you. So this is today, and I'm going to search for T. I can't see. TCRB. So it's currently under the ground. Okay, but this is really good, because what's probably going to happen is it'll probably happen in May or June or maybe July, and it's in the east right now, so this will be up all summer long to get a chance to look at it. Let me just go a little. So if I go up to about midnight. Okay, that's a little bit before midnight. This circle here is actually T Coronae Borealis. So let me zoom out just a bit. And what I want to do is I'll put some lines, which you won't have if you're looking up in the sky. So I'll put some constellation lines, and I'll put the label on. So you can see right here is Coronae Borealis. That's the constellation, if you're unfamiliar with it. So the reason I wanted to show you this is because this is a good way to find Coronae Borealis. So hopefully you can locate the Big Dipper, which is in Ursa Major. Here, I'll put the stuff on here. So there's the Big Bear, Ursa Major. And if you find the Big Dipper, and there's a handle of the Big Dipper, which is actually the tail of the bear here. And if you follow this curve around, the saying is you take an arc and it'll point at Arcturus. Now Arcturus is like the 4th brightest star in the sky. Okay, so it's really easy to see. It's going to be a reddish orangish star, and all you got to do is locate the Big Dipper and just follow it along, and you'll find Arcturus. That's the brightest star in the constellation Bootes. And then just to the east of that is Coronae Borealis. So it's this little U-shaped thing. It's not as, it's not terribly bright, but it's not hard to see. Okay, so you should be able to find it. All right, so let me close this up. And I go to current, right? And I got the wrong glasses on, that's the problem. I have two pairs of glasses, one for far away and one for close, so. Okay, that's better, now I can see. All right, so here you can see this again. So here's the Big Dipper. You follow the handle, go to Arcturus, and then just to the east of that is this, the Corona Borealis. And this is kind of a blow up of Corona Borealis. So that's what you'll be looking for. And I suggest that on the clear night coming up, that you go out and try to do this. If you're interested, especially if you're interested in seeing this new star, because what you'll see is Corona Borealis without the star there, right? And then all of a sudden there'll be the second magnitude star. Okay, so here's just this is not a real picture, but this is like the idea of where the explosion will occur. So that's T Coronae Borealis, and this is a real image, and you can see there's one star in Corona Borealis that's extra bright. It's called Alpha, and it's a 2.2 magnitude star. Now that's the brightness that this T Coronae Borealis is going to become. Okay, so this is an exaggeration. So if you see something like this, it's not going to be that bright. But this gives you a good idea. So if we look at this star here in Corona Borealis, which is right here, this is how bright it'll be. It'll be as bright as the brightest star, and it'll be right about here. So it's going to be very noticeable. If you get used to seeing this U shape, and then all of a sudden there's a star just like this, only right here, right? It'll be very noticeable. Okay. So I want to talk about right now how do we know that this is going to happen? What are the signs that it's going to erupt? So let me just show you. Let me just talk about what a nova looks like. Okay. So this picture is a nice illustration of what the system looks like. We have a red giant star, which is right here, and this is a binary star. So orbiting, they're orbiting each other, is a white dwarf. Okay. The white dwarf star is a very, very dense star. It's actually the core of a dead star that has lost all of its outer envelopes, and you can actually see the core of the star. Okay, so we won't see that, but because they're too close together. But there's this white dwarf that's orbiting, and if they're close enough, the white dwarf can pull material right off of the star. So all that has to happen is if the gravity out here on the big star at the edge is smaller than the gravity of the white dwarf, the material on the outside of the star spills over and falls onto the white dwarf. Okay. Now, a white dwarf generally is made up of carbon and oxygen. So what happens in a star is that, like our sun, for instance, it's burning hydrogen into helium. And after it does that and uses up all the hydrogen in the core of the star, then what happens is you got all this helium, the core contracts, and you can actually get the helium to fuse. And when helium fuses, you get energy out, but you also make carbon and you also make oxygen. So the reason you make those carbon and oxygen is because if you take a carbon atom and run a helium atom into it, which has 2 protons and 2 neutrons, you make oxygen. Okay? So you got this carbon and oxygen core, and it's very, very dense. So the size of a white dwarf is typically about the size of the Earth. Okay? That's not very big. and you have basically the mass of the sun in something the size of the Earth. So just one teaspoon of it would weigh tons. That's how dense it is. Okay, it's very hot, but there's no real hydrogen or anything here. All it is just an ember. So it's really hot and it is cooling down, right? But when you're next to this other star and you can pull off the outside of the star, regular stars are 75% hydrogen, 25%, roughly 25% helium, a percent or two of all the other elements that we know of, carbon, oxygen, iron, all this stuff. So when you're pulling this off of the star, you're pulling hydrogen off of the star predominantly. It comes pulling off, it spirals around in the gravitational well of the white dwarf, and eventually gets down onto the surface. Okay? The pressure and the temperature is really high on the surface. So you can do that for a while, but after you build up enough, you reach a critical density. Okay? And when you reach this critical density, what the critical density means is that you can fuse hydrogen into helium on the surface of this white dwarf. And it doesn't just do it slowly, it does it fast. It's like a hydrogen bomb going off. Okay? But it's not like a hydrogen bomb, like at Bikini Atoll back in the 1950s, blowing up a hydrogen bomb. This is a hydrogen bomb that's going to go around. Remember, it's about the size of the Earth in size, the entire star hydrogen bomb, right? All around the surface. So this huge explosion happens. It throws not only the material that was there, but also parts of the white dwarf out into space, which means we can learn some things about the white dwarf in an explosion like this, because we can see what's inside of it. Now, I just said carbon and oxygen, but we're starting to find out that when I said that, I said typically, because we're going to find out that there can be other things, right? And particularly neon, which is really interesting. Okay, so this is the mechanism. Okay, and of course, what happens is you have this explosion, and you can imagine this giant hydrogen bomb going off. It's going to destroy the accretion disk. It's probably going to, it's just going to throw material everywhere. And then it takes some time for it to start pulling the material back again, and it'll make a new accretion disk, and then it happens over again. It turns out that people think, anyway, that all novas are recurring novas. It's just a lot of them, it just takes a long time for them to recur. So the ones that we know that happen periodically are actually ones that are short enough period of time that we've actually seen it happen, right? So this nova was observed in 1866. It was observed in 1946. We're going to observe it this summer. And there's some indications in historical records that there were conversations with William Herschel back in 1787 about this strange star in Coronae Borealis that showed up, which fits exactly the pattern. And there's even some historical evidence from 1217 at a monastery where they wrote, and it was just like a year's end, making notes about what they saw and happened that year. And they mention some kind of strange bright star in Coronae Borealis, right? And it fits right in, right? So there's even some evidence back at 1217 AD that this happened. Okay. So let me tell you, I want this slide to kind of give you information about, this isn't a supernova, okay? This is a nova. So when you have a supernova, what happens is, especially a type 1a supernova, these are really important supernova because these are the type of supernova that they use to measure dark energy in the universe. Okay, they use them as distance indicators. And the reason it works is because when a white dwarf gets enough material so that its mass becomes 1.44 times the sun's mass, the electrons that are inside this white dwarf can't hold up anymore against gravity. They get forced into their neutrons, and well, they don't get forced into it. It starts to collapse. The fusion goes up, and you have all this carbon and oxygen, right? and carbon and oxygen just goes crazy, fusing all over the place. It blows the whole thing up. There's nothing left. It's just this huge explosion and nothing left. So this is it's really super, right? When they say supernova, it's super. So this is, I just put here the energy of an eruption of a supernova, of a type 1A supernova, is like 10 to the 44 joules. The nova, so I know it's hard to wrap your head around 10 to the 44 joules, but a classic nova like this is about 10 to the 38. So it's about 1,000,000 times less energetic than a supernova. It doesn't blow up the white dwarf, but it does blow up part of the surface of the white dwarf. Okay. So the type 1 is kind of I probably shouldn't have had this whole thing, but the idea is the mechanism's still the same, right? You have this white dwarf, and when it reaches 1.44 masses, solar masses, it reaches what's called the Chandrasekhar limit, and it can't hold up against gravity. So if you keep dumping mass onto this thing, eventually it gets up to this 1.44 and kablooey. You get a supernova, right? It turns out that it's kind of hard to do. Part of the problem is all these recurring novas. So if you have a white dwarf sitting there and you're dumping this material on, you can think, well, if I just have enough time, it'll dump finally enough material, and then we're going to get a type 1A supernova that explodes and blows itself up. But the problem is, every so many years, you have a nova, and the nova is throwing material out into space. So you dump material on, you have this explosion, out into space it goes, right? So it's really hard to build up the mass on the white dwarf. Even though we have a mechanism for doing it, it's because these explosions just keep throwing it back out again, right? So this is a big question. And in fact, it's such a question that people even, some researchers are even saying that this isn't the correct model for a type 1A supernova. That maybe it's actually two white dwarfs orbiting each other that finally collide together and make the explosion. Just because it's so hard to get this material, you can get it onto the white dwarf, but then it explodes, right, with a nova. So these are questions that people don't know, and it's really important because the type 1A, I don't know how much astronomy you guys know or how much you pay attention to, but things like dark energy in the universe are based on knowing the brightness of type 1A supernova. So we should really know what the mechanisms are that are happening. This is just a piece of the puzzle, right? What's going on with these nova. Okay, so let me just tell you how this works. I'm just going to do really just a couple slides. I just want to show you star formation. So what happens? So in dense clouds like this is the Orion Nebula, and this is the Eagle Nebula, because it looks like an eagle. So these are molecular clouds. They're cold, and inside of them, you get little overdensities. So the overdensities can become big enough that they get their own gravity and they start to pull themselves together, and that's how you form stars. Okay, so this is sort of the general picture of star forming. So imagine back here in this gas cloud, and you can see in here even some small stars starting to poke through the dust. So buried in here are brand new stars, right? They're starting to form, and they're hard to see because they're always buried in this cocoon of dust. But this is the general idea. You get a density, and then it shrinks down because of gravity. At the very center, it's really dense, and that ends up making a star. And then the other material falls in, and you end up with an accretion disk around the star just from stuff falling in, and then you end up with a planetary system like what we have, a solar system, right? So I think I'm not going to show this because it takes too much time, but when this happens, so this is a really nice picture, right? He's got this dense gas cloud. It's gravitationally bound and pulls itself together, and you make a star. The thing that stops the collapse of the gas is finally at the center, the temperature and pressure gets so high that you start to make turn hydrogen into helium, nuclear fusion. And that gives off the energy that stops the collapse. So then the star just sits there like our sun. It just sits there very happily, making this energy down in the core. It comes out the surface and it holds itself up against gravity. It's kind of odd because the gravity is what's causing the reactions, right? You're squeezing it down so much and the temperature and pressure is so high at the center that it causes nuclear reactions to occur. The rate that those occur depends on how much mass how hard you're pushing it down. So when you have a really big, massive star, it pushes so hard that the rate of nuclear reaction is just crazy, right? I mean, it's really fast. It just eats up its fuel really fast. And it has to do that in order to battle against gravity, right? So this is a nice picture, but it turns out that over 50% of the stars in the universe, or in our galaxy at least, are binary stars or in multiple systems. So what happens is when you see this collapse happening, it fragments. So rather than just the whole thing going down and making one star, you have this cloud, and it's not uniform, right? There's a spot over here that's a little more dense. There's a spot over here that's a little more dense. And when that happens, it collapses down and it makes two stars. But since it's part of this initial cloud, they're actually bound together. So you make a star, but they're bound to each other and they start orbiting, and that's a binary star. Okay? So, this is fine. You have binary stars, two stars. We don't have a second star, but we do have Jupiter, which is about, if it had been 1,000 times more massive, we'd have a binary star. But at any rate, a lot of these stars, over half of them in the universe have at least one partner. Okay, so here's sort of the way that evolution goes. So we first make, from the gas cloud, you make stars. If you have a sort of an average sized star like our sun, what happens is it'll use its fuel until it uses it up, and then kind of goes into this violent stage where it has like it's out of hydrogen. So above the core, it starts to fuse some hydrogen, and what it does, it makes the star swell up. So this is the sign that it's nearing the end of its life, right? So you end up with a big star. It still has the same mass that it had before, but now it's much bigger, right? So it's a red giant. This type of star, like I said, can make carbon and oxygen down in the core, but that's the end. So what happens is in the final death throes, when it's doing this, there's enough energy, it lifts off all the envelope of the star, and then you can see the core down, it becomes visible. So when you see the core, that's what we call a white dwarf. It's actually the core of a star. Okay, so in the more massive stars, they become red supergiants, and when they die because of a supernova event. So what happens in a core collapse supernova is that you build up iron finally in the core, and you can't get energy out of iron through fusion. Even though you could fuse the iron together to some other element, it's a endothermic reaction, so you don't get energy out. So that's the end of the star. So what happens is the core collapses, it goes down to a neutron star, the material above it falls down, bounces off of it, and boom, you blow up the entire star, right? So that's a supernova. Did you have a question? Oh, okay. I couldn't tell if you were. Okay. So that's for the massive stars. So let me show you here the HR diagram. And I'll get to the point of why I'm showing you this stuff. So the stars, so this is real data of stars in the sky. You can see this is luminosity, so that's how much energy a star is giving off every second. The sun gives off 10 to the 26 watts every second. 10 to the 26 1 watt light bulbs, 10 to the 24 100 watt light bulbs every second. That's it. So that's the luminosity. And over here, well, this is a color index, but what's more interesting probably is the temperature. This is the surface temperature of the star up here at the top. So we can locate where our sun is. The sun is a main sequence star. It's burning hydrogen to helium in its core. Right here, luminosity of 1. We would take this plot across and go over to here to the main sequence. The surface temperature of the sun is about 5,700 degrees. And if you look up here, you can see, sure enough, about 5,700. So we come down here, we go to 1. So this is where the sun would be on this plot. Okay. Now, when these stars die and they become, so the supergiants come from these really high mass stars. They're really big. And when they, as they're dying, they move kind of this way across the HR diagram and they become supergiants. And stars that are more similar in mass to the sun actually come up this way and they become giants. Okay, so they're still really big, but they're not as big as the supergiants. An example of a supergiant is Betelgeuse. So the red star in Orion, Betelgeuse, is a supergiant. If you put Betelgeuse in our solar system, Mars would orbit inside of Betelgeuse, I think. If I didn't look that up, it's something like that. Okay. The star we're talking about is a giant star in T Coronae Borealis, and it's about 75 times the radius of the sun. So that works out to about the distance of Mercury's orbit. So if you remove the sun and put this star from T Coronae Borealis in, it would reach out to about the size of Mercury's orbit. Okay, so it's big, but it's not very massive. It's only 1.1 solar masses, so it's only just 10% bigger than in mass than our sun. But it's in the dying stage, so it's up here. Where's my cursor? So it's up here. Now, when these lower mass stars, they form white dwarfs. And when you can see through the outer layers down to the core, then they immediately go from here way down to here, right? Because what you're seeing is, I mean, you're seeing the star, and then the envelope of the star starts to spread out, it becomes more transparent, and all of a sudden you can look all the way down to the core, and that's the white dwarf, okay? So that's located down here, and it's not very luminous. They're not very luminous. They're only about the size of the Earth. They are hot, but they're so small that they can't give off a lot of energy, okay? So they're really faint. Now, why does T Coronae Borealis dump this material onto this white dwarf? I mean, if this has been going on since they formed, you know, why something else should have happened. Maybe the giant would have given up all of its mass to the white dwarf. But there's a reason, and that's because, for one thing, this is a binary system. There's a white dwarf in it. That means that it's a more massive star, or it was a more massive star, right? Because the higher the mass, the faster you use up your fuel. So the white dwarf is dead, right? It's a dead star. It's finished its lifetime. So because of that, it must have been a more massive star. It lost all of its stuff on the outside. Now it's about 1.2 to 1.3 times the mass of the sun, but it's just this little white dwarf, right? That in size is about the size of the Earth, but really, really dense. So the white dwarf in this nova system it was more massive. It lost its outer envelope and it's way down here now. The other star is a giant, a red giant, like here on the diagram, and it started down here, and it has a mass of about 1.1 solar masses. So it's not different, a lot different than the sun, right? It just evolved away. The reason this happens is because all of a sudden you've taken something that would be about the size of the sun, and you made it 75 times bigger in radius, right? So when you do that, the outside of the star doesn't have a lot of gravitational force to hold on to it, and you have this white dwarf sitting there. So as it gets bigger and bigger, it starts to feel the gravitational force of the white dwarf and starts dumping material on. So almost all novas are in a system that's a white dwarf and a giant star, okay? As the second star starts to die and swells up, it can begin to dump material onto the white dwarf. Okay, so that's sort of the mechanism. Okay. All right, let me tell you just a little bit about this system. So it's a binary system. It's at a distance from Earth of about 2,600 light years. So we're about to see this explosion, right? It actually happened in about 600 BCE. Okay. And if you think about this, if you could actually trace the whole path from Earth to this system, you'd run into about 30 nova events along the way. Right? Because every 80 years you get a nova. So when you see it, it's not like tonight there was a huge thermonuclear hydrogen bomb explosion in T Coronae. No, it happened 2,600 years ago. It just took that long for the light to get here, right? So this stuff, is weird in astronomy because everything's in the past when you look far away, right? Okay, so one of the components is an M3 giant. It's got a mass of 1.1 solar masses, 10% bigger mass than the sun, a radius of 75 solar radii. Like I said, if you put it in the solar system, it would extend to Mercury's orbit, basically. The other component's a white dwarf. It's between 1.2 and 1.3 solar masses. The limit for setting off a type 1a supernova is that if this mass reaches 1.44, so if it accumulates enough, it gets to 1.44, boom, it's going to be the end of it. It'll blow up as a supernova. Okay? So it's a fairly high mass, and it's not that terribly far away from the limit where it's going to explode, right? They orbit at a distance of a half a AU. So an AU is an astronomical unit, it's the distance between the sun and the Earth. So we call that one astronomical unit. So it's about halfway between the Earth and the sun in distance. Okay. And you can see Mercury's at I think the AU for Mercury is about 0.37. So the edge of the star is at something like 0.37. The white dwarf is at like 0.54. So they're not far away from each other. And because it's a big giant and the white dwarf has a lot of gravity, it just starts pulling the material right off the giant star, just like in the picture here. The orbital period is 227 days. When it's stable, it's about a 10.2 magnitude star. And that's great because we do observations at MacAdam Observatory using the telescope and the CCD camera and filter system. And a lot of the stars we do are 10th and 11th magnitude stars. So as soon as I saw this, I thought, oh, wow, that's right in our wheelhouse. We can observe this thing. And what we're going to attempt to do is, when it's clear, get an observation, a series of observations every time it's clear and see what's going on with this, right? And it'll be great for our telescope. 10.2 magnitude stars, really bright for our MacAdam telescope. When it explodes, we're expecting to be 2 magnitudes. Like I said, it'll be about as bright as Polaris. And here's the kicker. It's going to last for about 1 week. This is just a big hydrogen bomb exploding. So it brightens up. You get a lot of light from all the material around it, and then it spreads out into space and it drops back down in brightness. So we got to pay attention. Okay? And you got to be quick about it. So if you hear that, if you're interested in seeing this star and you happen to hear that it went off, try to get out as fast as you can to see it. Because if you wait 1 week, it'll be already too faint to see. Okay? All right. So I wanted to put this in here because I got a lot of this information from Dr. Brad Schaefer, as I mentioned, from LSU. He had a paper in 2023 in the monthly notices of the Royal Astronomical Society, and he used data. I'm going to show you data that came from amateurs. Okay? They came from non-professionals. He uses the database from the American Association of Variable Star Observers, AAVSO. And this has been around, this organization, since 1918. And what happens is people observe things. They observe variable stars, they observe novas with their telescopes, right? And then when they get data, they send it off to AAVSO and it's archived. So it's hard to use because everybody has different telescopes and stuff, and it's hard to get it all on one system because they're different systems. But you can't beat this in terms of century-old data, right? And even farther than that. So this is what Brad Schaefer used. So let's get on to what we know about this eruption that's going to happen. So I want you to know, so wow, that's really psychedelic green or something. The green dots are meant to be visible through a visible filter, so sort of a green filter. The blue is through a blue filter. And I'm mainly going to just for this talk, I'm just going to talk about the blue filter. So it's showing the blue light, okay, rather than the green. Because it shows a little bit more detail. So here was the eruption in 1866, and there's actually data. There's V data at least. You can see this is the magnitude. It's hovering around 10th magnitude, but they caught this right when it exploded. Like most of these explosions, you don't know what's going to happen, and then all of a sudden, look at that, there's a star up there. You know, so it's all after the explosion when most of these observations are made, not before, because you don't know that they're going to go off. So here's all the way up to second magnitude. And then, of course, this is in years, a lot of years, but you can see it's just a spike and then it comes right back down, right? So here's the observation. This is in the green filter, the visible filter. This blue stuff, these blue dots are actually from photographic plates, and they scanned them and got blue data, so B filter data. And you can see, let's just see what happens here. So the blue's not quite as bright as the green. So we're down here at about 11.8 or something magnitude, and it's just kind of trucking along from 1895 all the way to 1935, and all of a sudden it shoots up right there. You can see the shoot up around 1936 or 7. So that's caught, right? Then the next thing that happens, about 7 years later, there's this huge drop off. You can see it just drops like a rock. So that's the pre-eruption dip. Okay. Almost, within a month after this pre-eruption dip, boom, you get the nova. Okay. So, and here's the nova going off in 1946, and then it comes back down and, continues on. So here is, again, this is from Schaefer's paper. Here is some other observations and now we're zoomed in more. So this is the 1940s, World War II time. So we got it coming along really well. This is that pre-eruption dip. And then just a few months later, boom, that's when you get the nova. And then this other interesting thing is this secondary eruption that occurs. Okay, so it's really bright. You got about 1 week where it's fairly bright, and then it drops right back down again. Okay, but within 100 days, about it makes a resurgence, a couple magnitudes brighter. So something's happening after the explosion. Now, this is why I really wish I could have showed you the animation of how inhomogeneous this explosion is, because the first explosion gives you this great big peak. And then there's a secondary explosion that comes out the poles where there's still some hydrogen left and there's still fusion going on. But then you get this really fast moving material coming out of the poles, running into the slower moving material. And this is possibly, we don't know, but this is possibly what's causing this secondary home. Okay, so right now we don't know. All right, just to show you one more time. So this is the data coming along, dropping down with the pre-eruption dip, and then up again. And here is the money diagram. So you'll notice the date now. We have 2010. So this goes back to about 2005. Again, this is the blue filter. So this is data from AAVSO, from just volunteer observers all around the world, sending their data to AAVSO. And the line here that you see on top of this is not a fit. Okay, it looks like, well, maybe you did some fit to the data and that line represents a fit. The line is 1946 or 1940, actually, probably starting about 1935, going through the dip and everything. So if you place this on top of the current data today, you can see we're at 2023 here. You can see how it comes along, goes up to this maximum that occurs about 8 years before the eruption, and then it kind of hovers along and then it drops off. So in 2015, people saw this and they said, it looks like T Coronae Borealis is going through this pre-brightening that happened back in,
Showing, it looked like the green filter was more bright. It showed more luminosity.
Yeah.
But the blue one looks like it's more sensitive
Yeah.
to pick it up sooner.
Yeah.
Is that accurate?
Well, that's what he says in the paper, that the blue is more. So one of the things that when we look at this system, you have a giant star, right? And that's giving off most of the optical light. The white dwarf and the accretion disk is giving off light, but it mostly gives it off in the ultraviolet. And it's not nearly as bright, right? Until you reach the point, then it gets really bright. But so it could be that we're getting some light from the accretion disk, maybe, because it's going to be hotter and they'll give off blue light. The other thing that Schaefer talks about is that he thinks that dust might be being created. And so you get these dust particles that condense out of the material. And he talks a lot about that it could become really dusty. Blue light is affected more by dust than visible light. So that might be why the effects seem to be bigger. That's what he sort of is postulating, I think. Anyway, you can see here's the dip, and boom, there's the eruption. Okay. So from the
Why is red light not represented? Other things.
Most observers have a visible filter, and a lot of them, some do have blue. It just depends on. I mean, there are. I think there are observations in the red and in the infrared. It's just there's not as many, and they're not of the same quality. I think B and V are like kind of standard. Especially V is a very standard filter, and especially. Yeah, remember, this data is all amateurs, right? So they have their own telescope, they have their own CCD camera, and they probably have a V filter.
You gotta take it.
Yeah, and you have to calibrate it, right? So you have to have stars that you calibrate off of, and not all the stars around in the area are going to have R or I filter systems. In fact, in a webinar that he did, there were people asking questions, and they said, "Can we use the Sloan Z filter, right? It's part of the gun filter set. And is that okay to use? It's just in the kind of intermediate infrared." And he said, "No, don't do it. There'll be nothing to compare with. So your data will be the only data. We won't compare because nobody else is going to have that filter, right?" So it's really, I think, just that the V and the B are like really, in old times, that was like, it's a really good temperature indicator. So if you do V minus B, you get this color index, and that really correlates well with temperature. So B and V are fairly nice filters, but the V is the one most people use. Okay, so one last thing. Here's the sign that it's a binary. So the way this works, and this shows better in the green. This star, whenever you have a giant star, there's all kinds of stuff going on. You have big convection zones, you get like eruptions from the surface of the star, You just get all these kind of random things going on. But underneath this, you can see the sine function, right? And this is the stars orbiting each other. So you get a maximum when you see the giant star at the edge like this. It has a teardrop shape, right? That gives you more light. So that's during the maximum. As this rotates around, you can imagine, rotating this star. So this isn't an eclipsing system, so they don't block each other ever. They don't eclipse each other. But if you bring this around, you see just the nice round backside, and that's not as bright. So anytime that we're sort of perpendicular to the system, you get this teardrop shape, and it gives you more light. So you can figure out the orbital period, because here would be a maximum. So you'd see it in this configuration. Now imagine this orbits all the way around, gets to the other side so that we can see the teardrop, but now it's on the right-hand side, right? It's going to be a maximum again. So you'd have a maximum, and then you have another maximum and a minimum in between. And then, we get back to our original configuration. So these peaks are just half an orbit. So you have to multiply it by 2 to get the orbital period, which is 228 days. So it's very clear. I mean, the data really shows it has an orbital period. They finish their orbit like we do in 365 days. It does it in 228 days. Okay. But the other thing that he was showing here is that both the green, so you can see this is 2023.5, right? Halfway through 2023. And you can see how this thing's really doing well going along in both filters. It's more ratty in the blue, but then everything's dropping off right at 2023. That's the dip. So this is the dip that happens before the explosion. So we have at this time, it was about 8 months until it was going to explode. So he gives the time as plus or minus 0.3 years. So plus or minus about 4 months, right? So it could happen today. It could have happened a week or two ago, but we have until about September. It's not expected to last that long. So my guess is it's going to be May or June, maybe July, when we see this thing go off. Okay, any other questions on this? Yeah. When I get to that slide, I'm going to show you. We don't know.
Okay.
Nobody knows. This is unusual data. I mean, we don't have a lot of data on this kind of stuff. And unfortunately, I mean, it could be the case that the dip happens and then it goes back up to the same brightness, right? And there's no explosion. But the fact that you can see it we're due for an explosion, and the dip happened in 1945. So, it looks like it's about gearing up to do this. So, but the dip is not clear. It's not clear why it dips before it explodes. Maybe we'll learn something from this. Okay, so why is this event interesting? So in red, I put it's very rare that we have the predicted time of when the explosion is going to occur. Almost everything, supernovas and novas, you see the bright star, or it shows up somewhere in a survey or something, and then everybody turns their telescopes to it, and you start seeing what's going on. It's all post-explosion, right? We had a chance to see what's going on pre-explosion, and that doesn't happen very, very often. So I'm hopeful that this thing doesn't go off until about June, because we can get some data, we can see what's going on. We're also working with MacAdam Observatory, and we talked them into getting on their target of opportunity. So the 2.7 meter telescope at MacDonald is going to be ready to go, hopefully, when the explosion happens, and we can get spectra of this explosion, right, at MacDonald Observatory as well. So let me just run through these questions. What causes the brightening 8 years before the eruption? So that's that first thing. What causes the pre-eruption dip, which is what you just asked, right? What causes the secondary eruption about 100 days later, right? So we saw that secondary peak. Is dust formation important? If we get enough observations at different wavelengths, we can tell if it's dust, if there's a lot of dust in the system. Okay. Is a white dwarf an unusual oxygen neon dwarf? Which it might be. Okay. Can TCRB ever become a type 1 supernova? And how are type 1 supernovas created? That's the big thing, right? Because we want to see how does the mass get transferred onto these things. Does it lose more mass during the explosion than it gains for the 80 years before, right? If it's losing more mass, you're never going to create a 1.44 solar mass white dwarf that explodes, right? It's just going to keep doing this nova thing over and over. So here's the best we can do. There's a paper out that this 8 year before the eruption was actually, they said, a dwarf nova. So what happened, the dwarf nova is like a nova, but rather than the whole system just exploding, right, with hydrogen bomb across the whole surface, sometimes you can get localized hydrogen if a clump sort of falls onto the star, and you can get an eruption, and it's called a dwarf nova. So this paper was pretty convinced that that 8 year previous increase was due to just being a dwarf nova. The problem is that it happened in 1945 and it happened in 2015. They're like identical. So that doesn't look like some kind of random event that just gives you a kind of an outburst that's a dwarf nova. So that might not be the case. What causes the pre-eruption dip? I don't even see any speculation on this. It's that bad. But like I said, there are, especially when the nova happens, but hopefully there's people doing this before. There are already targets of opportunity in on the James Webb Space Telescope, the Hubble Space Telescope. There's even a neutrino array, and I don't remember the name, neutrino array, that's going to be looking to see if, because when you have a hydrogen bomb explosion, you get neutrinos out. And they're hoping that they'll see detection of neutrinos coming from this explosion. There are satellites, observatories all around the world waiting for this, right? And I think some are observing ahead of time. So we might have a good chance of seeing what is causing this pre-eruption dip. But at the moment, we don't know. Is the white dwarf an unusual one? An oxygen neon. So I told you several times that a white dwarf is typically carbon and oxygen, right? That's what's inside of it, carbon and oxygen. Turns out that if a star is massive enough, then rather than just stopping at carbon and oxygen with its fusion, right, and that's the end of the star, and then you see the carbon oxygen white dwarf. Instead, what happens is that it can do a little more fusion, and it can actually turn the carbon into neon. Okay, you just have to add another helium nuclei onto the oxygen and carbon. So some of these stars can actually go a little bit longer and make neon. So this is a big surprise because people didn't expect neon to be there. But this star had spectra taken in 1946, and the spectra wasn't that great. There was some indication that at the location where neon emits, that there might have been some emission from neon. This has been seen in other oxygen neon dwarfs or white dwarfs. In fact, 10% of white dwarfs are believed to be oxygen neon. Okay. Can this ever become a type 1 supernova? So one problem is there's some theoretical papers that say an oxygen neon white dwarf can never become a supernova. And the reason is you need the carbon. The carbon is an accelerant. So what happens is when you reach that limit of 1.44 solar masses, the carbon helps in this really rapid fusion that just blows the whole thing up. Without the carbon there, it's a slower process, and you may not be able to get a supernova out at all. Now, there is some indications that this might not be the case. In fact, there was a paper talking about the Crab Nebula, which I always thought was a core collapse. The Crab Nebula was a big supernova in 1054 AD that had a lot of recorded history. A lot of people saw it. You can see it during the daytime, right? It turns out that people are starting to think that it might be an electron capture supernova. Now this makes a big deal because we're looking at type 1a supernovas, assuming they're all carbon oxygen. That there might be some of these that are actually oxygen neon. So they don't quite know how the explosion occurs. What generally happens is when you reach the 1.44 limit, the electrons actually fuse into the nuclei and it makes a neutron star and you do get a supernova. But there's a remnant left. There's a neutron star. That's what's believed right now. And the Crab Nebula is believed to be one of these. So how are type 1 supernova created? This is a big deal. We need to know how much stuff is coming out during this explosion. Are you losing more than you gain for the 80 years that's been dumping on there, right? Because if you're losing mass, you're never going to be able to add and get it up to a type 1a supernova. Okay, so these are big questions. So this I just put again, this is, I really appreciate, he's really the guy. I mean, if you read anybody's references about this upcoming event, it's Brad Schaefer. I mean, he did all the work. He knows this is happening, right? Okay, so from his talk, I swiped this from his talk, and this is where I wanted to bring this out for you guys. The public, and if you're interested in this, and if you're interested in watching, you can be a part of trying to help discover when the eruption occurs. Obviously, the eruption occurs in just a few hours, right? So we need as many eyes on the sky as possible. So if you're out and, you know, if you kind of get into the habit of it, oh, it's a clear night, you know, I think I'll go out and look at Corona Borealis, you know, looks fine. This is why you want to get used to what it looks like. You know, another night, oh, it's fine. Maybe some night you're coming home and you look up and it's like, wait a minute, what's that star? It's not as bright, but there's something there, right? And then you watch it and it gets brighter and, you know, you're seeing the eruption. So it's really important for scientists to know when this eruption precisely occurs. And they have the AABSO has a website where you can submit. If you happen to see it happening, submit it and say, hey, the eruption's happening, so that the people know, right? But he does warn very carefully, make sure you know that it's actually happening. There are planes, there are satellites, there's all kinds of things that if you're not paying too close attention, you look up and be, I think it went off, you know. They don't want the whole world to be notified falsely. So you look at it, and this is why you need to know ahead of time. You need to know what that Corona Borealis looks like every night. And then all of a sudden, oh my gosh, there's a star right there that was never there before. You can go to the website and report it. Okay, it'd be huge help. This other stuff is they're asking for all kinds of observations. BVR, not so much RI, but definitely the B&B, because that can go right up against the old data, right? So the B&B data. We want to do a lot of this before the eruption so that we can see what is happening in the dip. And like I said, we're going to be looking at spectra and we're going to see if we see neon emission coming out when the explosion occurs, because that's a clear sign it's an oxygen neon white dwarf. So this will be really interesting. So here's MacAdam Observatory. So we're going to dedicate time to observe this. And I just want to show you this. Our new website will probably change it up some as time goes by, but this is our T Coronae Borealis website. It talks a little bit, and down here, this is. I want to turn this into a thing where we're always showing the current data that we're gathering at the observatory. So this is not T Coronae Borealis, but this was data that we were doing for our Lyra variable on March 28th. And here is a variable star that's brightening up and going through its maximum phase. These are the reference stars. So you can see the reference stars are very stable. And this is a huge peak for TV links. So that was something I did with a student just recently. And what we intend to do is every night when we observe, using the telescope. We'll have a current page, so we'll upload whatever we have. Right now it'll be T Coronae Borealis. And what I hope to do is you show like one observation, and the next time it's clear, we can get some more observations, and we'll just accumulate it. And I'm kind of secretly hopeful that since we can do, I don't know if you see this, these are error bars on this. I mean, we can get really high precision at our telescope, really high precision measurements. So I'm hoping that maybe there's going to be a slower incline that people don't know about before the big eruption, right? So we can watch this and maybe for a week or something, it'll start to go up a little bit. In which case we'll put it not only on the website, but we'll say, hey, it looks like it's brightening up. You might want to go out and watch and see if it's about to erupt. Okay. So we're going to be doing this interactively. We'll keep updating it. We're going to put our data there, and you're welcome to come back and visit day after day if you want, whatever. So it'll be there for you to see. What happened to my slides? Oh, go back here. Okay. So when this happens, we'll have some kind of special sky talk or something, and hopefully set up some telescopes and look at this and stuff. We'll announce it. We have to move fast. When it happens, we'll have to do it within a day or two, probably, because that's when it will be the brightest. So maybe it won't work. If we got a lot of cloudy weather, it won't work. But anyway, that's the idea. Okay, I wanted to say one last thing. I think especially you Sky Talk regulars know Dr. Gary Perlin here. He was just telling me the other day we were talking about this, and he said he spent a summer at MacAdam Observatory. He was a graduate student at the University of Texas, and he spent a summer at MacAdam Observatory because there was this Nova Cygni in 1975, and the director at the time said, we got to dedicate McDonald telescopes to doing this. So he asked Gary, will you go out and observe during for the summer, right, in beautiful Fort Davis, Texas, on top of mountains? And he's like, sure. Austin is really hot and humid in the summertime. Fort Davis is beautiful in the summertime. So he went out there, he did photometry, he used the 2.7 meter telescope, and this and this neon 3. And when they published this paper in 1978, he said that people told him there isn't neon in white dwarfs. I don't know where you're getting this from. This is wrong. It's not neon. It can't be. There's no neon in white dwarfs. So there is. So I thought I'd just throw that in. We'll be using the same telescope if McDonald agrees to this, which I think they are. So here's my end. Here's our observatory. We'll be using this. We're going to, whenever it's clear, we're going to EERI data. We'll give us a series of it each night. It's clear. And like I said, we'll keep posting it to you guys. You can come back and look at it. And, you know, I really think if you're here because this is interesting to you that a new star is going to show up, a bright star, right? Go out ahead of time, because it wouldn't be. Remember, the one star in Coronae Borealis is a second magnitude star. So if you have no clue what it looks like and you go walking out and you say, okay, well, there's 2 stars that are kind of bright, it won't mean a lot, right? But if you see this constellation over and over, and you see the one bright star, and then all of a sudden, boom, there's a brand new star there, right? That's how you'll really get the best experience, I think. Okay, so that's it. Any other questions, or I'm happy to answer anything? Yeah.
Abstain.
Oh, yeah.
Is there a specific instrument or telescope that you're most excited about that we didn't have last time?
Well, definitely the space telescopes that are able to do X-ray. So maybe Fermi or I don't know. According to the talk that I heard, I mean, basically all of these satellites are on on alert, right? So you have like SWIFT that does, well, we need a UV and an X-ray observation because that's the explosion, right? And it's going to be in X-rays and even gamma rays. So that's going to be exciting. The thing is, what's beautiful about this is that it's not everybody reacting, right? It's not like, hey, Nova went off and everybody tries to quickly go and get data. We know it's coming. And so everybody can be prepared and you can do pre-observation. So I think the X-ray UV, I think this neutrino, they're going to watch the neutrino detectors to see if they're actually getting neutrinos from the eruption. That's pretty cool, I think. So there's going to be so much data that's what's really exciting. I think they'll be able to decipher a lot of what's going on. Yeah.
Oh, for the extra credit.
Yeah. Can you hang on for 1 second? I'm not sure. I'll be right. Yeah.
Although most novas go off, like you're saying, scrambled, get data, that's what we have. Novas are not anywhere near as becoming supernovas. There must be another few novas or something that have a known recurrent cycle.
Oh, yeah.
to them. Do any of those have the same kind of brightening and dimming patterns as this nova? Is that standard of novas, or is this one weird that it has that pattern?
I think they have pattern like I gotta honestly tell you in all honesty that I haven't done a deep enough dive to answer that question. But I think there are things that happen like this in other nova. And you're right, there are recurring nova. There's like about 5 fairly bright ones that happen every 50, 60 years. This is kind of an unusual, for one thing, is because it's got the biggest separation just about. The longest orbital period and the biggest separation. Most of the nova are much closer to the star. So in my way of thinking, and I don't know if this is right or wrong, but in my way of thinking, being farther away may allow it to have a more stable type of nova experience, right? So maybe that allows it. It might affect it. It's not. Most of these, the recurring ones, are not at 0.5 AU. They're some of them are right inside the giant, basically, right? So this is kind of an unusual star system, right? So I don't know the answer to that, whether they see all the same thing with other ones.
So, say too late. Thank you, speaker. Here's the website to show you there's a monthly all-sky finder chart you can print out.
Oh yeah.
Just hold it up, and
Yeah.
The timing is set as soon as you get started. That's why the time is through the summer.
It's right here. April 1, May 1, June 1, July 1.
Those are just PDFs, so they look a little odd. East and west are reversed because it's supposed to hold up like this. And east has to be the eastern sky, and the western sky has to be the western horizon. So
This is sundown, right? It's sundown.
here's the time, 10 p.m.
10 p.m. So you can see in July, Coronae Borealis is going to be right up there, high up in the sky in July, at basically sundown.
It's raining outside. There's no clear skies. If anybody that would like to tour these, living home be warm. Okay.
What did I do to stop? So I should probably go. Hey, my screen isn't a touch screen. There.